Advent of open standards and modern development frameworks, building complex systems is becoming easier by the day. In this session, we'll be exploring how AsyncAPI and Spring Cloud Stream makes development of event-driven microservices easy and friendly for developers. Hi, my name is Giri Venkatesan. I'm a developer advocate at Solace and happy to be connecting with you at AsyncAPI Conference on this session. We'll take a real-world scenario as a use case and explore how the requirements are met by the use of AsyncAPI and Spring Cloud Stream throughout this session. Let's consider Smart City, a contemporary concept that we are all familiar with. Smart City is a framework that utilizes information and communication technologies to develop, deploy, and promote sustainable practices to meet the urbanization challenges. Right? It requires smart solutions to manage the needs around energy, mobility and transportation, health and education, and various other aspects that formulate smart city. Right? As we speak, we have numerous functioning smart cities that are successful around the world: New York City, Singapore, Amsterdam, Helsinki, Zurich, and many others too. Key enabler for the success of smart city is open data. Let's talk about open data a little bit. Historically, governments, enterprises, and individuals have held their data close, sharing as little as possible with others. True impact can be realized only when all the participants in an ecosystem share data and information, leading to the ability to make informed decisions jointly in real time. And smart city definitely needs open data. Open data is, in a sense, redefining this entire digital transformation across the ecosystem. For our session, we'll be examining the needs, probably I would say a specific subset of a mythical smart town where APIs are a way of life, to demonstrate AsyncAPI and Spring Cloud Stream, what impact it has on the EDA. Right? Though the smart town requirements are exhaustive, for this session we'll be looking at a subset involving temperature monitoring and management. This involves receiving and processing temperature readings from various sensors deployed across the town, parks, public facilities, vehicles, and so on. We'll also be building services to simulate the temperature sensor readings and generate operational and aggregate alerts as events. With that said, let's analyze the possible interaction between the services and the application in this context. The controller interaction with energy management system is to affect temperature changes. Obviously, it requires a synchronous request response interaction based on REST APIs. It's great. The rest of the interactions can be event-based, meaning asynchronous, and can use PubSub operations mediated through the intermediary, what we see as an event broker, right? So in this case, the events are published around temperature reading and various alerts. Services and applications create their subscriptions and consume these events when the broker delivers to them. Event gateway, essentially an event broker, mediates the interaction between the publishers and subscribers and offers decoupling and subscription-based event routing. Okay? So this is what makes up an event-driven design for a particular problem around temperature monitoring and management. Okay. Here's a fun question for you. APIs are only asynchronous in EDA. Is it a fact or is it a myth? Right. So you have 10 seconds. So please give it a thinking, and let's see if you get it right. All right. It is a myth. Simple reason is digital transformation journey is nothing but an adoption of event-driven architecture on top of existing architectures. This could include harmonious interaction between microservices and applications in an ecosystem. So it can be asynchronous as well. It can be both synchronous and asynchronous. Let's talk about async APIs. Async API is an open source initiative that seeks to improve the current state of event-driven architectures. That's great. The goal is to make working with EDAs as easy as it is to work with REST APIs. That goes from documentation to code generation and discovery to event management. Right? So most of the processes that you apply to your REST APIs nowadays are applicable to event-driven asynchronous APIs too. So the async API specification settled the base for a greater and better tooling ecosystem for the EDAs. So that's the foundation, or that's the purpose of async API. Right? Let's look at broadly at the APIs and the API specifications. APIs are nothing but application programming interface, right? They make it easier to exchange information between applications, tell you what kind of information to be passed as a request and what to expect as a response, and so on. API consumers at any point in time don't need to know the how part of the implementation. It's completely hidden from them. It is true for both synchronous and asynchronous APIs. The operation-wise, in a synchronous context, you will be invoking the APIs, whereas in a asynchronous context, you would be either publishing or subscribing events. So only the operational terminology changes, but they are still APIs. In essence, building APIs can be tough and time-consuming. Absence of standards and tools can make it even more difficult. Here comes the specification. We have Open API specification for the synchronous APIs, aka the REST APIs, and an async API specification for the asynchronous APIs, in this case, event APIs, right? And then if we, extending this further, API standards and specification help the developers with tools to generate documentation and code, as well as acts as a repository for lookup at runtime. So instead of exchanging this API specification on a informal medium, now you have a centralized repository where they can be looked up, and they are standards-based. That means tooling ecosystem can evolve to generate codes for various frameworks and so on. Let's see how the asynchronous API draws a parallel to the synchronous APIs. Both of them deserve a portal, right? In the case of synchronous, we call it an API management portal. And then in the case of asynchronous, we should call it as an event management portal, because the interaction is completely based on events being published and subscribed, right? So both synchronous and asynchronous APIs needs a centralized portal for managing APIs, right? It starts with cataloging, versioning, and maintaining the APIs, essentially a public repository that can be queried at runtime. A specification is also required. We have Open API for synchronous APIs and Async API for the asynchronous APIs. And then when it comes to tooling, Swagger is a tool for generating code from the specification for REST APIs. And Async API is also a tool that can be used to generate code for asynchronous APIs. When you look at the generated code, here's where the difference comes in. When it comes to REST API, it's a simple client-server interaction on a protocol, which is a single protocol, that is HTTP. So the Swagger generates the client stubs and server stubs from the specification. When it comes to Async API generates code for the widely used frameworks like Spring, Node.js, Python, and so on. And then it also supports various protocols, AMQP, MQTT, WebSocket, and so on. The simple reason for multi-protocol support is underlying broker that's offering this publish subscribe capability might be supporting or might be requiring support for various protocols. So it automatically gets bubbled up and supported at the code level. All right. Now, another quiz. The statement goes like this: I will have to redesign my REST-heavy architecture from scratch to adopt EDA. Is that a fact or a myth? Let's see. You have 10 seconds. Just take a shot at it. And it is a myth. Simple reason is, the REST-heavy interaction and asynchronous interaction can coexist. Nothing has to be dropped. Nothing has to be adopted from the scratch. So a digital transformation journey is basically, adopting a new architecture with its legacy infrastructure still in place. So you don't need to redesign your architecture just to adopt EDA. All right. Let's get into a bit of a comparison and working together. The 2x2 table or map on the left-hand side clearly indicates what tool to use for what purpose. Synchronous point-to-point or one-to-one straight away, it's REST API using OpenAPI specification. For anything asynchronous, it is AsyncAPI. All right. On the right-hand side, let's kind of explore a real-world scenario, an e-commerce application, and see how the synchronous and asynchronous nature of interaction comes into play. There are applications we are looking at, order management system, warehouse, and product catalog management and marketing operations, right? So these are already existing in the infrastructure, and they have already exposed REST APIs for applications and services to interact with these systems, right? Now let's take a look at it. Every single interaction might end up in generating an event, right? For example, a new order placed on the order management system could publish an event, could publish an event called received. And then when the order is processed, it could publish an event called processed, and so on, right? So these events could be either triggered in response to a request received from other services and application, or could be a notification event, response to some change within the application systems. Among the events generated, it's quite possible to identify and expose certain high-value events that may be of interest to both internal services and applications or external applications. All right. This is nothing but event enablement, and it's a first step in the event enabling process. All right, so let's take a look at this. When you look at this picture, we have these products. It could be internal or external. Delivery service provider, he needs to know about when an order is shipped or processed so that he can pick it up and then initiate the shipping. Similarly, price comparison tool could be an external product that need to operate only on the product that are promoted for sell status. So that ready to sell event is published from the product catalog, right? So you can see here the events acts as a bridge between these applications and the products, utilizing this asynchronous nature of communication, right? So here the REST APIs and the event APIs can coexist. We'll have a quick demo on AsyncAPI. For a quick demo, we will check out the standard tutorial/demo that's in the AsyncAPI website. It's about streetlight systems that's publishing the environmental lighting value to a broker. Right? The technology that we'll be using is Node.js for the code and Mosquito as a broker to provide the PubSub service. Right? It simply publishes the event, basically like a fire and forget. There's no other processing involved for simplicity's sake. And here is the AsyncAPI specification file. You can assume it's pretty much hand-coded. This section clearly indicates the AsyncAPI version, and then more on the application details. And this server construct indicates how to make connection to the broker. Mosquito broker that can be located at this URL using MQTT as a protocol and so on. And the channels is nothing but a collection of topics that this application can publish or subscribe to, right? So here is a channel name, nothing but a topic name. An event can be published to this topic with a message whose structure can be like this. So it's a message. Its payload is of object type and contains properties like ID, lumens, and sentAt, and their attributes and description and so on. And one thing to notice, the operation ID is an attribute that give a hint to the code generator what to call the function that publishes this event. All right. So once the AsyncAPI spec is ready, we can put it through standard process. I'm just going to gloss over certain steps like installing AsyncAPI code generator, and then creating the AsyncAPI spec as a file, and then running the code generator. It's nothing but AG is the tool name, the YAML file, and then the template. So this template can vary depending on what output you want. In the case of Node.js, it's Node.js template. In the case of Spring, it will be Spring template and so on. And the output directory and a few specification around the server type and so on. So this will generate the full-fledged code for this Node.js framework, and it's available for us. Okay. And at that point in time, you can simply start the generated code. Of course, if you want to implement your custom business logic for event processing, you can go ahead and do that. Otherwise, a standard functionality would log the messages received on the application, right? So you start the application and continue to publish. You should see events being exchanged, subscriber and publisher in action. Let's go and check it out. I'm going to switch context here. So I have 3 windows that's already open and ready to go. So this is a command you would be used to generate the Node.js project code base, which is already done, as I mentioned. Here is the code. I'm going to simply start the application. Okay. It subscribed to this. It made a connection to the MQTT broker, sorry, Mosquito broker, and it subscribed to this topic light measured. And in this window, I'm going to publish an event like on the topic of light measured and specifying host information and the message payload in the form of a JSON. Okay, let me just publish it. So you can see the published event is received here. And similarly, I can also create another subscriber, MQTT subscriber on the same topic. I keep the subscriber also ready and running. Now I'm going to publish one more event. You can see both the AsyncAPI generated code as well as the command line MQTT subscriber. Both of them will receive this event. Yep, there we go. All right, so that's the quick demo that I wanted to show around AsyncAPI. Spring Cloud Stream. The Spring Cloud Stream is a framework for building highly scalable event-driven microservices connected with shared messaging systems. It also provides components that abstract the communication with the many message brokers possibly out there away from the code. Right? It uses features of Spring Boot, Spring Cloud Functions, Spring Integration, and Spring Messaging, making it a part of the broader Spring stack. Right? One of the key benefits of using Spring Cloud Stream is instead of having to learn messaging APIs of different broker systems, developers just have to understand the communication model that Spring Cloud Stream supports. When it comes to the communication model, there are 3 supported models, but the support for each of them varies from binder to binder. First one is the publish subscribe, which is a traditional one. Subscribers are independent from each other and receive events in order. Right? Then consumer groups, basically a fan out and load balancing option across multiple consumers. The last one is stateful partitioning support, basically that brings about the in-order processing for consistency and performance. To sum it up, it's a framework for building highly scalable event-driven microservices that is connected to a messaging system and making use of the publish subscribe infrastructure. Right? We'll see more on that. So the other key component of Spring Cloud Stream is the Spring Cloud Functions. Right? Spring Cloud Function basically promotes the implementation of business logic as Java functions. Right? By doing so, we are decoupling the development lifecycle of business logic from the specifics of runtime broker, so that the code can run as a web endpoint, stream processor, or a task, and so on. Right? It also allows us to enable Spring Boot features such as auto configuration, dependency injection, metrics, etc. So let's look at the message exchange contract as a Java function. We have 3 functions. First one is supplier, nothing but an event source. In messaging term, it will be a producer or a publisher of events. The next one is a consumer. That will be an event sync. Could be a subscriber or a consumer of events. Right? And third one is somewhat unique. It's a function, nothing but a processor. It simply consumes an event from the underlying broker, processes it, and can produce an event, basically published back to the broker. Right? So the Spring Cloud function forms this essential methodology for implementing your messaging requirements. Okay. Let's look at the key components of a Spring Cloud Stream. A binder. A binder is really the one that makes a difference and makes the framework useful. They provide an abstraction layer between your code and the messaging system through which the events are flowing, right? And there are many binders. Few of them popular ones are binders for RabbitMQ, Apache Kafka, Apache Kinesis, Google PubSub, Solace PubSub Plus, Azure Event Hubs, and so on, right? And next one is a bindings. Is a collection of interfaces that identifies the input and output channels declaratively. It acts as a bridge between external messaging system, a hosting, a queue, or a topic, etc., and an application provided producers and consumers. A channel simply represents the communication pipe between the middleware and the application. Essentially, it's an addressable component made available by the server where events are organized. Okay. And schema is used for serialization and deserialization, and it defines the object structure of the messages being exchanged as a request or a response. These are typically objects, but also supports primitives and arrays. Last, message. The data structure used to communicate with the bindings between your code and your message broker. It's basically the mechanism by which information is exchanged via a channel between the server and the application. It must contain a payload. Optionally, can also contain headers, right? It contains data as defined by the application, which must be serialized into a format that's understandable by either the application and or the broker. JSON, XML, Avro, binary, these are the formats. Right. We'll have a small Spring Cloud Stream demo. For the Spring Cloud Stream demo, we'll be using the Getting Started tutorial from the VMware Spring Cloud Stream web pages. What we're going to do is we're going to download a Docker image containing RabbitMQ and Kafka applications, and then run that Docker. And when the Docker comes up, obviously we have the message broker RabbitMQ ready for use. And we'll create a Spring starter project with the dependencies on the Spring Cloud Stream and RabbitMQ binder. And with that, we'll create a simple Spring Boot application and start adding message exchange contract, nothing but the Java functions that can that's basically the consumer bean with a name toUpper. So at runtime, the Spring Cloud Stream will interpret this as a subscriber that subscribes to a topic by name toUpper, and then it follows a certain convention that will be that will result in toUpper-in-0 as the topic name. So A, it will create a topic, and B, it will create a subscriber to the topic. Right? Whenever an event is published to the topic, the underlying message broker will automatically deliver to that subscriber, which in turn will be consumed by this function. When the function receives this message or a string, it will simply print out toUpperCase. So technically, if something is published on this topic, we should see an uppercase converted string getting printed on the console when the Spring Cloud Stream project is up and running. Right? It's a very simple one, but it demonstrates this aspect of Spring Cloud Stream function, Spring Cloud Stream, Spring Cloud function, and then the implementation of message contract, and in turn going through the binder to create necessary message broker specific artifacts like topics, queues, and so on. And at runtime, when message appears, it's getting routed to this function seamlessly. In this entire exercise, we'll be focusing on building only or implementing only the business logic. Okay, so let's get started with downloading the Docker YAML file. It's already there. I am going to download this. Got it. and I'm going to run the Docker. We'll bring up the Docker. So you can see when the Docker starts, it's starting the RabbitMQ, Kafka, Zookeeper, and so on. All right. So it's ready. Now let's go and check the RabbitMQ console. It's available on this particular port. It's ready. Now we will have to go to this Exchanges tab to see if there are any topics, right? Yeah, these are all topics that's existing. These are system topics. There is no user-created topic at this stage, all right? So this is good. Now RabbitMQ is ready. Let's go ahead and create a Spring Cloud Stream project. Let me just make it bigger so that you can see things. So what we're going to do here is we're going to create a new Spring Starter project and name it as SCS Getting Started. That's all right. And we will choose the dependencies. Obviously, we want Spring Cloud Stream, and also we want the binder for RabbitMQ. Okay, chosen these dependencies, and we just create a project. It's going to do all the work of creating project, setting up the configuration. Let's just quickly review the POM file, which should indicate that we got our Spring Cloud Stream dependency made available in the class path, and also the binder for RabbitMQ available. All right. Let's open the application main file. So we have this function. Now this is the one that's going to be invoked. And at this point, we need to implement the Spring Cloud function to create consumer. All right. Let's go back and check the documentation or the tutorial. You can see here, we have done this part. We just need to implement a consumer. All right. So let's copy paste this. And paste this. Here you can see these are unresolved. Let's resolve them. It is annotation, and the consumer is nothing but a Java util function. So that's all we have to do. Let's save it and let's run it as a Spring Boot app. Okay. When it's running, I'm going to maximize this console so that we can see clearly. Okay. Let's go ahead and publish an event to this topic. As a convenience, the RabbitMQ portal provides an interface for us to publish an event ad hoc basis. So let's go into this topic, and you can see here test publish. So I'm going to put a all lowercase hello world. Let me publish it. So you can see that message is successfully published. So what it means is this message got published to this topic, and then in turn the messaging broker sees that there is a subscriber with a subscription for this topic, and it delivers to that subscriber. In our case, that subscriber is nothing but the Spring Cloud function, and it should have received a message. Let's see here. There we go. So the message got routed to our Spring application based on the subscription it created. Right. So again, going back here, all we did is we implemented the business logic by implementing this bean function called consumer, and then we followed a nomenclature that's suitable for our application. We just said to upper. If you had called it as a process temperature or something, it would have created a topic with a different name. And everything underneath what happens under the message broker is hidden from us. As a developer, we would be still looking at as if we are doing a pure Spring application using all the aspects or the features of Spring, like Spring Cloud Functions, Spring Cloud Stream, Spring Integration, Spring Messages, and so on. Right? But behind the scene, the Spring Cloud Stream takes care of working with the underlying message broker via the binders that's made available on the class path. EDA can help prevent cascading failures in a microservices architecture. Is it a myth or fact? Let's wait and see. All right. It is a fact for sure. The reason is in EDA, all the interactions are mediated through an intermediate messaging broker. So that creates a decoupling. So a failure never can affect another service and so on. Right? In real world, EDA is pretty much useful and has found a good footing on various industries ranging from capital markets, retail banking, manufacturing, and so on, wherever there is a need for real-time messaging, right? The takeaway when you work with EDA and open standards, here is a small subset. Open standards benefits the customers or businesses from by preventing lock-in with the vendor, and this whole community-driven model has its own advantages. The best of the minds come together to create the standards and build the ecosystem. Increasing adoption in the industry is an indication that it is something to reckon with, and the resource pool, knowledge base, and all those things continuously expands. And growing interest in the tech community widens the reach and expands the resource availability. And last but not least, this whole notion of being open and community-driven fosters innovation. Let's revisit the smart town that we kind of checked out in the early part of the session. In this picture, we can clearly see there's a REST-based interaction and event-based interaction. Both are coexisting to bring about a solution for temperature monitoring and management, right? Let's dive in a little bit deeper into each of these microservices. The first one is a data simulator. Basically, in a demo setup, we can have a sensor publishing data. So we have a program that's going to publish temperature reading periodically. So it's a microservice that uses the Spring Cloud Stream supplier contract, message exchange contract to publish temperature reading. And one thing to be noted here is all these microservices are implemented using Solace Cloud PubSub plus broker as the messaging broker. So many of the terminologies and the convention that you see are specific to very specific to Solace and pretty much common across the messaging brokers as well. So what you see here is a topic name on which the temperature reading will be published. The topic name itself carries contextual information like the city, latitude, longitude, and the temperature. This comes in handy when you want to create a subscriber based on wildcards and so on. Right? And the next one is a data collector. It's a microservice that uses Spring Cloud Stream's processor message exchange contract to subscribe to temperature events and publish operational alert events. And you can see the topic on which it's being published. This is also a microservice that is built using Spring Cloud Stream. And the third one is IoT data collector, data aggregator. This is a microservice that uses a Spring Cloud Stream processor exchange pattern, where it subscribes to these operational alert events and publish an aggregate alert. In terms of processing, it accumulates the operational alerts generated for a period of time, say 30 seconds or a minute, and then aggregates the temperature value and publish a single event, right? These are all operating on Solace Cloud PubSub Plus Broker. Smart Town demo will be running pre-built microservices that uses Solace PubSub Plus Broker on cloud as the messaging provider. Before we run these services, we'll take a quick peek at the PubSub Plus Broker and its event portal so that we get an idea. Solace PubSub Plus Broker offers an event portal that allows developers and architects to collaborate and design applications, events, and schema, right? And catalog and publish them, publish high-value events as event APIs. Download AsyncAPI specification of these published events. At this point, all the tools that AsyncAPI has to offer can be put to use in terms of validation, code generation, and so on. And from that AsyncAPI, you can generate a Spring Cloud Stream projects that uses Solace as a binder, Solace PubSub Plus Broker as a binder, to create a complete, ready-to-use microservice application that simply requires business logic implementation. The portal is a tool that helps the architects to design the entire EDA, starting with an application domain, which contains one or more applications. Just acts like a namespace. And each of these applications in turn contain information about the events that it can publish or subscribe to, right? And as far as the events are concerned, the event schema, the underlying schema that a message payload is expected to carry at runtime is also specified here. Without writing a single line of code, this designer tool helps the architects to design the entire EDA all the way down to the schema level. Once this is done, the catalog feature kind of lists out the published, lists out all the available events and their associated applications with their topics, right? This makes it searchable and queryable and so on. And last but not least is the event API product. It is nothing but the identified high-value events in the EDA can be exposed for external access via AsyncAPI. You pick and choose the events from the EDA that you want to expose with the appropriate permissions for publish or subscribe and make it available as a downloadable AsyncAPI specification. And with that, the AsyncAPI takes over and start building code using the tools, start building application, and straight away you just have to implement the business logic. Let's quickly review the Smart Town microservices design. So we have 3 microservices: a data simulator, collector, and aggregator. Right? Simulator is the one that simulates the sensors by publishing temperature reading. Right? And data collector subscribes to this temperature reading and produces operational alert. And aggregator is the one that's going to accumulate these operational alerts over a period of time and produce an aggregated alert with an aggregate temperature, right? So in this case, when we completed the exercise of event portal, right? Let's take a look at this. We published an event API product. That API product is basically exposing these events with a permission set. In essence, temperature reading, if an external application wants to subscribe to it, it can. And if an external application wants to publish an operational alert to the broker, it can. So this event API product revolves around these 2 events with a permission set as permissions as described here, right? And this async API specification is available. You can download from the portal. If not, you can. It's made available on a public URL. When you expand and see, you would get all the necessary details about the constructs that are part of the async API specification: channels, service, messages, and schemas. Right. So at this point, let's go straight into the Spring tool suite, and we have pre-built microservices except for the collector. Let's review them. When you look at the Spring Cloud Stream project, at runtime, the behavior is controlled by this application YAML, or it could be application properties. It contains all the necessary information for the Spring Cloud Stream to operate the publish subscribe activity. Right? So you can see here, to begin with, the underlying binder, the type of binder, and then the environment properties for the binder to make the application to make a connection to the message broker and so on. This will be specific to binder use. And then the bindings properties, whether it's a publish activity or a subscribe activity, depending on whether you see an in or out on the function name, and also the topic on which the activity takes place. Right? Anything above is just a plain Spring Boot startup parameters. Right? Let's take a look at the application file. This is a classic Spring Boot application. The only function that we added here is the bean function. Just looking at the signature, we can see that it's implementing this producer message exchange contract, right? So whenever it's invoked, it's going to construct this POJO, what is temperature reading, and appropriately populate attributes and publish it to the broker. Before publishing, it sets the header property called target destination and sets the topic name, which is constructed based on the city, latitude, and longitude values at runtime. Okay, so let's start this application and see where it goes. Sorry, it's running. I'm going to stop and restart again. So, city IoT simulator. This is going to simulate temperature reading data being published. Yes, it is being published. Let's not worry about it. We will figure out a way to verify this. And then the next one is based on the picture. What we see here is data collector. Let's park this for a moment. Let's go to data aggregator. This is also a completed service. Let's review that. So, right, let's take a look at the aggregator microservice. Let's review the application YAML file. So you can see the bindings properties calls out clearly both input and output, or in and out events, message names, and the topics on which the publish and subscribe activity takes place. So the function name is aggregate temperature, and the binder properties are appropriately set, basically to establish connection to the underlying broker. Let's look at the application file. Just ignore the flux and mono use here. What we're saying here is we're going to get a sequence of operational alert over a period of, I believe, 10 seconds, and accumulate them, and then put it through a mapping process to calculate the average temperature. After computing such a value, we are going to construct a POJO by type aggregate alert, and then set it as a payload and publish a message to the broker. And the target destination is going to be the one that is as defined in the application YAML. Here it is. Aggregate alert created v1, and it's going to contain values like city, priority, and type. All right. It's going to be the analytics. All right. So when this event is published, obviously there will be some subscriber, and in our case, based on the picture, we have a dashboard application. In our case, we are going to be again building a simple web app that subscribes to this event on the broker via MQTT protocol and just plot them on a Google map. So that one, probably there's nothing big deal. We just need to run and visualize them. What's the key thing here is the data collector. Let's go back to the AsyncAPI portal, where the event portal has published the event API product, and the corresponding AsyncAPI document is available for download from this location. It contains all necessary details, right? So with that, let's see if we can generate the code. Here it is. So I already installed the AsyncAPI code generator, and you can review the parameters here. The output folder, and then everything with the -p is a parameter. View is provider, binder is Solace, dynamic header type equal to header, artifact ID, package name, and so on, right? All these things put together, when you run this, it's going to generate a complete Spring Cloud Stream project. We only have to implement the business logic, basically the bean function, all right? So in keeping in mind time constraint, I've already completed that. So I'm going to review that with you here. Alert generator, and you can see here in terms of application settings, it's pretty much similar to what we saw in other examples, and it uses the message exchange pattern, what we call as a processor. And let's look at the application. When it produced the code, probably it wouldn't have had any of these things. It would be an empty body, right? Now we have populated the business logic, basically to open up the temperature reading data and check the temperature and see what range it is in, and based on that generate or appropriately assign the alert type and severity, and create a POJO operational alert, add it as a payload, and publish to the specific destination, right? So now we know that it's already there. Now, before we run a completed one, let's start the alert aggregator. So the expectation is it should not be able to proceed much further because it's not going to get any events, right? So over here, we are running a simulator that's simply publishing temperature reading. And over here, we are subscribing to operational alert, which is not yet coming through, right? Only when operational alert comes, it can process and produce an aggregate alert. And this is the aggregate alert application window, alert generator. I'm going to run the application. Let's see. So it should subscribe to temperature reading. All right, there we go. Yes, it is getting the temperature reading data, and in turn, it's producing operational alerts. There we go. Now that when in a period of 10 seconds, it received 8 operational alerts, and from that, it was able to construct the severity type as high and alert type as high temperature, and publish this aggregate alert events. All right. Now, this is the window where I can run the web application. This is going to subscribe to this aggregate alert and just plot them on a Google map. All right. Let's see. Unfortunately, there is an issue with the Google Maps key. I could not show it in a live map, but this is just a representational image. When I ran this program with multiple cities publishing their temperature data, aggregated alert data, we were able to see the severity and alert type all in one place. So pretty much what we have done is, going back to this picture, we took care of this one subset of problem of temperature monitoring and management, more specifically everything around microservices, using AsyncAPI and Spring Cloud Stream with Solace as the backing broker. Right. That brings us to end of this session. So I hope you were able to get a kind of big picture on how the AsyncAPI and Spring Cloud Stream work together to make this EDA building exercise easy and friendly for everybody. Thanks very much for the opportunity.